So previously we talked about a chunk of metal, a conductor, that is moving in a magnetic field and how that induces a potential difference that we call EMF, or motional EMF. Now we're going to take that conductor and we're going to put it on a rail. All we're trying to do is actually connect one end of the circuit to the other. However, there's a challenge here that we can't just put a fixed wire here because we actually need this to be moving. And we need the rest of the circuit to not be moving with respect to the magnetic field, because you can imagine this wire here is also a chunk of conductor in magnetic field. So it's important that the rail isn't moving with respect to the magnetic field, but this is, and so that's why we think about the circuit this way. We need part of it moving, part of it not, so we slide a bar on a rail. So the rail is providing the path for charge to flow. It's the wire. And we've said that the sliding bar has motional EMF curly E, and so that becomes our delta V. And so we get a current where EMF was given by VLB, where L is this length here, B is the uniform magnetic field you're in that's perpendicular to V, which right now we're assuming is constant for this analysis. So we get a current flowing due to this charge separation. And again, this charge separation only occurs in this conducting bar because that's the only part that's moving. So we now have a circuit. We have a closed loop through which charge can move. Now notice that there is a resistance here. So what we typically do, again for simplicity, is think about the resistance of this wire. We might explicitly put a resistor in there, but we usually think about this bar as not having resistance, again, for the sake of simplicity and ease of analysis. So now let's think about why the bar is moving. We've said, oh, it is moving, but there actually needs to be a force applied, and this is pretty interesting. So something has to be actually pulling the bar to the right, like a hand or a motor, whatever you want. But something literally has to be pulling it to the right. Otherwise, it wouldn't be moving at a constant speed. Why is this? Well, there's a second force, which is a magnetic force. Remember that you have a magnetic force on a wire, which is going to be given by Li cross B. And so if we think about this I and then look at B, this force here is again the magnetic field on the wire, that's going to be to the left. So if we just gave this bar a kick and started it moving, even if we said there was no friction, it wouldn't keep moving at a constant speed because there's actually a force due to the current that we've induced in this circuit, right? Remember that the current's going the rest of the way around. That this current in this bar, right? So we're only talking about this object, will have a force to the left. So you actually have to pull it to the right, but you can actually balance these forces. Again, if we say that V is constant, well, you know then that the forces acting on the bar, that was a bad sigma, that your forces acting on the bar equals 0, right? F net equals 0. So that means that whatever force you're pulling with is going to be equal to the force of the magnetic field to the left, as long as we say that our that our velocity is constant. So we can actually use that to understand how hard we're pulling it. But again, that is assuming that it's moving at a constant speed, which is what we want to do for thinking about having a constant current, constant EMF. Now, one thing that I want to mention is you might think, oh, well, it will slide back the other way if I let it go, nice and simple. Interestingly, the magnetic field, the force from the magnetic field always opposes the motion, right? So imagine instead that we're pushing it. So that would be a velocity this way, to the left. So in that case, when you do V cross B, you now have your charges going this way, where we're imagining them positive. So you end up with a positive charge there and current flowing the opposite direction. What that means is if your current is flowing this way, then when you do again I cross B, your magnetic force is to the right, opposing your push. So whether you are sliding the bar out or in both cases, you have a magnetic force that is going to oppose that motion due to the current that's induced. Again, we can just say that F net equals 0, meaning that V is constant, and that's usually the starting assumption we use. If V is constant, then F net is 0, then F push, again, however you're actually making this move, is equal to the magnetic force in magnitude. Okay, so make sure you think through this and understand the directions. We now have multiple forces happening here. We have the force that's separating the charges, we have a force that's being applied, we have a force that's actually then on the object itself. So the separation force is on the charges, not on the bar, but then these forces are on the bar itself. So make sure you understand what object it's acting on. Now, one cute thing here is we can think about power, the power you're putting into the system and the power that's being used by the system. So if we think about our forces here, again, we're going to have a constant velocity, that's our starting point, so we know that net force is 0, so the magnitude of our pulling and our magnetic forces acting on the bar must be equal. Now, we know that the magnetic force is ILB. The point being that you can pull it however hard you want, but if it's a constant speed, constant velocity, then pulling force must equal the magnetic force, which we know exactly. Then I was induced, right? So remember that I was induced, and so I becomes this more complicated thing, and then we multiply it all together. So to figure out how hard you must be pulling it, if you have a constant velocity, it depends on the velocity, the length squared, the magnetic field squared, and the resistance. And again, we normally associate the resistance with the rail that it's sliding on, assuming that it's fixed. So that's force, that's not power. What's interesting, we usually define power as energy per time, but it also can be defined as force times velocity. So if we just think about our power input, capital P in this case is for power, we can multiply the pulling force times the velocity that we're pulling it at. And now we get this form, lots of stuff squared over resistance. Okay, that in itself, it's an equation, it's not that interesting. But then we can say, where is that power going, right? Power represents a rate at which I'm putting energy into the system. Now we have to be able to account for that energy. It's either being used or stored. So if we then think about electrical power, i.e. the dissipated power due to the resistance of our system, that's I squared R. We haven't even made necessary, well, and this is assuming an ohmic system once you do that. So our dissipated power, basically due to the resistor converting electrical energy into heat, I squared R, and when you multiply this out, you get this again. So it's interesting in that we actually have these two being equal. We see that the power that I'm putting into the system by pulling or pushing on the bar goes into the resistance, dissipating it into heat. So all that means is that physics works, really. We don't see power disappearing or appearing, and we also aren't storing it anywhere in this situation. And remember that capacitors are something that store energy. So you could think about power going into storing energy in a capacitor, but we don't have one here. So these match, which is nice. This is what we would expect. So we've used two different ways to get there. Everything works out. Okay, so what? Why do I care? Basically, this is a generator. We've said that by putting a mechanical force on this bar, by pushing or pulling it, we're creating electrical energy, which can then be dissipated through electrical processes. So instead of thinking about that just being dissipated by this bar having a resistance and therefore creating heat, we can put a light bulb here. And as I push and pull this bar back and forth, current will flow back and forth. You can't imagine just pulling it one way, but eventually you'd probably run out of wire. But as you're making current go either direction, you light this light bulb. So this is the definition of a generator. We are taking something mechanical, we are taking motion and turning it into electrical energy. So induction, and we'll talk more later about specific generator designs, but this is the basic idea.